In this video, we're going to talk about isotopes and average atomic mass. Dalton was wrong about all elements of the same type being identical. Turns out atoms of the same element can have different numbers of neutrons. And remember, neutrons weigh something. They have a relative mass of 1. So if you have different numbers of neutrons, you can have a different mass number. Elements that have different mass numbers due to different numbers of neutrons are called isotopes. An isotope is an atom of the same element. It's the same element because it has the same number of protons, but it has a different mass due to varying numbers of neutrons. So we name isotopes by putting the mass number after the name of the element, like hydrogen 1. This is an isotope of hydrogen that weighs 1. And it would look like this. It would have 1 electron, and hydrogen would have 1 proton, which is why it weighs 1. If I had an isotope of hydrogen called hydrogen 2, I would have to add a neutron into the nucleus. The nucleus would look more like this. It would weigh 2 because the proton weighs 1 and the neutron weighs 1 for a total of 2. Remember, electrons weigh nothing. Hydrogen 3 would have to have 2 neutrons and a proton to weigh 3. So how heavy is an atom of oxygen? And the answer is it depends. It depends because there are different kinds of oxygen atoms. Most people would probably just go to the reference table and look up oxygen and look at its mass number. But that mass that is on the periodic table is not a mass of an oxygen atom. It's the average mass of all of the known isotopes of oxygen that are in existence. So we're more concerned with the average atomic mass than the mass of any one atom. So the average atomic mass is based on the abundance, or the percentage, of each variety of that element in nature. We can't just simply add up all the isotopes and divide by how many there are because they exist in different percentages on the planet. We also don't use grams for this mass because the numbers would be too small. We use a unit called the atomic mass unit, or AMU for short. It's defined as 1/12 the mass of a carbon-12 atom. So if you divide 12 by 12, you get 1. That's where we get this relative atomic mass unit of 1. And we just compare all the masses to that relative unit to come up with numbers that are a little more easy to work with. Each isotope has its own atomic mass, so we determine the average from the percent abundance. And this is how we do it. There's 3 steps and an unofficial 4th step that I'll talk to you about later. So step number 1 is turn the percent abundance of an isotope to a decimal. So to turn it to a percent, they had to multiply by 100. You just need to turn it back into a decimal by dividing by 100 or moving the decimal 2 places to the left. Step number 2 is to multiply that abundance as a decimal by the atomic mass that's given in the problem. Step number 3 is add your results. So here's an example problem. Calculate the atomic mass of carbon based on the naturally occurring isotopes. So remember, step 1 is we want to turn the percent abundance that they gave us into a decimal. So 98.89 becomes 0.9889. And I did that just by moving the decimal 2 places to the left, or in my calculator dividing that number by 100. 1.11% becomes 0.0111%. A common mistake I see kids doing on this problem is just to move the decimal in front of the number. Remember, you have to move the decimal 2 places to the left or you didn't do it correctly. Carbon-13 has a percent abundance of 0.01%. As a decimal, that would be 0.0001. Step number 2, we want to multiply that mass that's given in the problem by the abundance. So 12 times 0.9889 is 11.86. 14 times 0.0111 is 0.1554. And 13 times 0.0001 is 1.3 times 10 to the negative third. Step number 3, all you need to do is add them up. So you add all those numbers up and you will get 12.0167 AMUs, atomic mass units. Okay, step number 4, the unofficial 4th step is check your answer. How can you check your answer? Well, the reference table has the answers. So you have to show your work in these problems because the answers are all in front of you on your reference table. If you go to carbon on the periodic table and you look at the atomic mass, that mass number on top, that is the average atomic mass of all the known isotopes. And our number is close enough for our purposes. I only had 3 isotopes of carbon. In reality, there's probably a couple more. So if your answer is close or exactly what the number is, you know you did your math right and you can move on to the next problem. If your answer does not match the reference table, you know you did it wrong. And the only way that you're going to get a wrong answer is if you leave that wrong math on the paper. You probably made a mistake with one of your decimal points. Go back and fix it till the number matches. Okay, now you try. Element X has 2 natural isotopes. The isotope with a mass of 10.012 AMUs has a relative abundance of 19.91%, and the isotope with a mass of 11.009 AMUs has a relative abundance of 80.09%. Calculate the atomic mass of this element. My suggestion to you is to make a little chart like I did on that last problem and go ahead and give it a try. Pause the video, and when you're done, unpause it and I'll show you how to do it. Okay, so here's my chart. Here's my 2 isotopes, and I have a column for their atomic mass unit, which was given in the problem, and I have a column for their percent abundance, which was also given in the word problem. So step number 1 is we want to turn those percent abundances into decimals. So we just move the decimal place 2 places to the left, and I get 0.1991 and 0.8009. Step number 2 is to multiply the mass by the abundance. So 10.012 times 0.1991 and 11.009 times 0.8009. I'll get that number and that number. Step number 3 is we're going to add our results. Those 2 numbers added together is 10.8105 AMUs. Because this is an unknown element, step number 4 is a little different. I can't go to the reference table and check to see if the numbers match, but our new step number 4 is going to be, does your answer make sense? Well, let's look at our 2 isotopes. I had an isotope that weighed 10, and I had an isotope that weighed about 11. And our abundance was about 80-20. 80%, or the vast majority of these isotopes, weighed 11. 20%, the minority, weighed 10. So would it make sense that our answer of 10.8 is closer to 11 than it is to 10? Of course. And that's how you're going to do step 4 on a problem like this. Okay, let me show you what these problems look like on a Regents exam. So the table below shows the atomic mass and natural abundance of 2 naturally occurring isotopes of lithium. So we see the familiar chart like you saw before, and instead of asking you to just solve, they want you to pick which numerical setup can be used to determine the atomic mass of naturally occurring lithium. So there's 2 ways to do this problem. One way is to memorize those 4 steps that I gave you and look at the math that is shown in these 4 choices and see which choice follows those 4 steps. Which one is doing those steps correctly? And another way to do this would be to do the math of these 4 choices. If you punch all of these math operations in your calculator, you'll get 4 answers. And you can go to the reference table and look up lithium and see what it weighs on average and compare your answers. The correct one will be the one that matches the periodic table's answer. Well, let's look at number 1. They took 7.6 and multiplied it by 6.05. Well, the percent abundance was 7.6, and that's a percent. They didn't change it to a decimal, so choice number 1 is no good. Choice number 2 looks like they did. They took 7.6 and turned it to 0.07. Did they move it 2 places to the left? Yes, they did. And they multiplied it by the mass. Let's see if they made a mistake on the second one. I doubt it. 92.4 was the percent abundance, and they changed it to 0.924. So it looks like they're doing step 1 correctly. The multiplication here is showing our step 2, and the addition sign is showing step 3. So choice 2 is our correct answer. Choice 3 and 4 are completely wrong. And these are, when people get these questions wrong because they have no idea how to do them, they will usually pick something like choice 3 or 4. It looks like they're dividing by 2 because there's 2 isotopes. Now, you know when you calculate averages, you divide by your sample size. If you were given 2 tests and you got a 100 on one and a 90 on the other, you add the 100 and the 90 and divide them by 2, and that would be your test average so far. That's not how it works with isotopes. Because they don't exist in equal amounts, in equal percentages, you cannot simply divide by the number of isotopes. So those are there to trick you. Please don't ever pick choices like 3 or 4. Let's try the next one. The table below gives the atomic mass and the abundance of 2 naturally occurring isotopes of bromine. Which numerical setup can be used to calculate the atomic mass of the element bromine? And it looks like the answer is choice 3. So choice 3 is taking the masses, 78.92 AMUs and 80.92 AMUs, and multiplying them by the natural abundance, but as a decimal, not as a percentage. So choice 3 is our correct answer here. So, isotopes are atoms that have different masses due to different numbers of neutrons. That is a definition that you just need to know for the Regents exam. Because there are many isotopes in existence, this makes discussing the atomic mass of any one element difficult. Instead, we opt for calculating the average atomic mass based on the percent abundance of all the isotopes that we know of. This involves a 3 or 4 step process that you need to memorize. This is very typically on the Regents exam, and it's one of the only math things that we learn throughout the year that you can't look up the formula on reference table T. This is just a process that you need to know. So I hope you practice it, and if you need any help, please let me know.